Hello everyone, my name is Anurag Kaur. I'm a research scholar for Punjab University, India. I'm very thankful for this opportunity to present the topic titled as an algorithm combining an optimized hybrid block method with cubic trigonometric B-splines based differential quadrature method for solving Hunter-Saxton equation. This is the overview for the presentation. Let's start with the introduction. Hunter-Saxton equation is a non-linear PD which was firstly considered by Hunter and Sexton, and it is given in equation 1 where t and x are the time and space variables respectively. It has many real-life applications and few of them are listed below. Solution U of Hunter-Saxton equation corresponds to splay waves that propagate through the liquid crystals molecule. This equation describes the orientation waves that cause declinations throughout the crystal structure. HS equation modeled as high frequency limit of the shallow water equation, Kamasa-Horn equation, which models soliton as well as breaking waves. This equation describes geodesic flow on the diffeoformism group of unit circle. Many numerical methods have been applied on the HS equation and few of them are listed below. Semi-analytical differential transform method, a finite difference scheme, Haar wavelet quasi-linearization approach along with the finite difference scheme, A-domain decomposition method, paired approximation technique, collocation methods based on cubic trigonometric B-splines, quintic B-spline collocations, Chebyshev function, Laguerre wavelet, barycentric interpolation. Collocation methods used by Param requires an initial guess for the startup of the technique, so it is not an independent method. To solve nonlinear PDEs, most of the numerical methods use linearization scheme first to deal with the nonlinear term. Also, very small time step size is used to obtain the better accuracy. So, our main aim is to employ a simple, cost efficient, and efficacious method that will overcome the above listed drawbacks. In this work, we consider the combination of the differential quadrature method and an optimized hybrid block method. To the best of our knowledge, neither DQM nor hybrid block method have ever been used for the HS equation. Let's start with the DQM, differential quadrature method, which was firstly introduced by Bellman. Later, Kwan and Chang improved it by finding the weighting coefficients. Xu gave the recurrence formula for higher order derivatives. To find the better approximation, several types of trial functions have been used, like Lagrange interpolation, polynomial, B-spline basis function, and many other. In order to implement the differential quadrature method, consider the discretization of the space domain into equidistant n plus 1 nodes where step size h is considered. Trigonometric B-splines functions are defined and modified as in following reference. Table 1 lists the value of trigonometric B-splines and its derivatives at nodes. This is the table. Further, it is modified as it given in equation 2. So the set MTB0 to MTBN constitutes the basis of a domain. Now assuming U to be a sufficiently smooth on its entire solution domain, the approximate values of the derivatives with respect to x at point xi can be computed as given in equation 3, where Q denotes the order of derivatives and Aij's are weighting coefficients. Now, following the procedure given in the following reference, weighting coefficients of first order derivative can be computed. Further, Schu's recurrence formula is applied to obtain the weighting coefficients corresponding to the second order derivative as given in equation 4. So now we have obtained all weighting coefficients. Now using them, we have approximated the partial derivatives. So now using DQM, we have transformed the PD into system of ODs as given in equation 5. Now we have incorporated the boundary conditions with it. Therefore, this is the required system of ODs. In this algorithm, time stepping scheme considered for HS equation is hybrid block method. Using the concept of interpolation and collocation, an optimized one-step hybrid block method for IVP has been derived in the following reference and has proved to attain the characteristics such as zero stability, consistency, convergence, and irrestability. This is the required formula. After applying this to the system of ODs, we have solved it by using fsolve function in of MATLAB software. Now we are going to discuss about the stability. Hybrid block methods are astable, consistent, and convergent as proved in the following reference. If the system of OD is obtained after the implementation of DQM is stable, then algorithm presented is unconditionally stable. So in order to prove the stability of the system, stability of corresponding linearized system of OD is investigated. We assume a constant equilibrium solution of HS equation UEQ. So linearized equation corresponding to the non-linear HS equation is given uxt plus u equilibrium and u double derivative with respect to x equals to 0. We have plotted eigenvalues of the coefficient matrix for different values of n in figure 1. As all the eigenvalues have negative real parts, so the system ODE is stable. Therefore, algorithm DQMOHP is unconditionally stable. This is the graph. Now, we are heading to the numerical experiments. In order to prove the efficiency of the presented method, we have applied this method on three numerical problems. Using MATLAB, numerical results are obtained. We have used L infinity for error determination. We have used the L infinity formula, and to calculate the time convergence rate, another formula is used. So, firstly, test problem 1 is considered as this. By taking n is equals to 79, table 2 tabulates the result absolute error for t equals to 1, where we have taken just 10 times step size. As step size is equals to zero point 0.1, we have taken 10 time steps to obtain these results, which are significantly accurate. Time convergence rate in terms of L infinity is calculated and tabulated in table 3, where you can see that order of convergence rate is around average of 5. 3D plot for the problem 1 is given in figure 2 till time t equals to 1. Now we are heading to problem 2, which is considered as this. Boundary conditions can be extracted from the exact solution. Each of the table results lists the results obtained in a single time step only without compromising the accuracy. That means three tables have been shown which have been evaluated just in one step, one time step. Now we are heading to test problem 3. We have considered this problem in order to compare with the other numerical methods. Comparison of the results of numerical methods, this and that of algorithm DQMOHP for t equals to zero point 0.1 is shown in table 7, where we have taken n equals to 128 and 5 time steps are taken. This is the results. These are the results, which shows that they are very much better than the others. Table 8 and Table 9 displays absolute errors for t equals to zero point 0.01, taking 5 time steps, and for t equals to zero point 0.001, taking 1 step respectively. The results predict the advantage of higher accuracy of DKM over the other collocation methods, as you can see from the tables. Convergence analysis performed for DQM-OHB is shown in figure 3 with consideration of the maximum limits of the compiler. This is the graph, and this is the 3D plot for the problem 3. Now we have summarized the results and conclusions. Numerical experimentations of the presented method on the Hunter-Saxton equation highlights the efficiency of DQM over the collocation methods performed so far in the literature. Order of convergence rate with respect to time for DQM-OHB is around 5. Unconditional stability is proved. To solve non-linear mixed derivative PD method does not require any linearization scheme or any initial guess, hence it is a direct method. This work widens the scope of hybrid block method in the field of partial differential equations. These are the references. Thank you so much.